Hi, Philippe. Thank you so much for joining us to discuss your work.
Hey, Allison, nice to meet you, and thanks for inviting me.
We're going to be discussing multi-turn accuracy with LLMs. Before we dive into the details of that, though, tell us a little bit about your journey into machine learning and into this space specifically.
I'm originally French, and I moved to the US for undergrad. And in undergrad, I got very interested in research. And in particular, I think I was very interested, this isn't like between 2012 and 2016, I started getting very interested in text analysis, in what's called NLP, natural language processing. And, I thought, wow, like this field is going to really evolve. Like it's still very basic, the kinds of things we can do with text. And I knew I wanted to do research and go do a PhD, but at the time, I didn't have much experience in NLP, and maybe you take one class, but that doesn't make you an expert. But I pretty quickly figured out I wanted to work in the intersection of NLP and interfaces. So how do we build more futuristic text interfaces or like text heavy interfaces? And on a whim, I kind of applied to PhD programs, kind of describing some of these ideas. And at the time, it was a bit of a gamble. I was like, either I'm going to get in, and then somebody understood what I was saying and like is interested in helping me figure this stuff out, or they're going to be like, this guy's a little bit crazy, and then I'll just won't do a PhD. It's not for me. Luckily it worked out. I found advisors that were really supportive of what I was thinking about, and I think it's much harder to get into PhD programs now. It's gone very competitive, especially in AI. And so I think like from there, I worked quite a bit on NLP tasks and connecting it to interfaces and things like this. And it is machine learning, but I'm more on the applied side of machine learning. I think like I try to always think about, okay, what are the kinds of new ways we can evaluate these models that are more realistic or going towards realistic evaluation. None of my work is yet, wow, like, okay, now we get it in the hands of tens of thousands of people. And that's really the gold standard at the end of the day. But it's somewhere on the spectrum going towards there.
That can bring us right into the motivation. So tell us a little bit about, and we can kind of talk about the problem space and how that leads to the motivation of this paper.
Yeah. So, I mean, I can tell you the fun backstory of the work.
Yeah.
So Hiroaki and I, we're two co-first authors on the paper. We were good friends, and he did his PhD at CMU while I was in Berkeley, and we met each other at conferences. We were both working on summarization, which is this nice little neat NLP field. And he joined Salesforce Research at the same time as I did. Like we graduated around the same time. And we always thought, okay, let's work together. Let's do something fun together. That's what researchers do. If we like each other, we try to collaborate, see how that goes. But unfortunately, we were in different teams and there was different priorities. And he slowly became a really expert at programming languages. So, building models specific for programming languages, which I never got into. So then we kind of drifted apart, right? And which happens. A few years in, we're like, we should still work together, and so we got on a call and we're brainstorming ideas. He's talking about what he's now an expert at, which is like PL, right? Like programming language tasks. And he tells me, eval of PL is totally broken. And I'm like, well, eval in general is pretty broken, but what do you mean? So he kind of like says, well, one of the most common benchmark is human eval. Human eval, for listeners, if you don't know, is a very popular OpenAI. OpenAI created this benchmark. It's very small. It's only 90 samples. And they kind of curated this list of 90 samples of like Python programming functions. Like the instruction is basically like a doc string. So here's everything you need to know about the function. Here's the function header, the parameters, etc. Even sometimes here's examples of input and outputs, right? And so it's a very well-defined problem. And then the models have to generate the function. Hiro was saying like it's broken because it's too easy. So it's too easy in that realistic programming task, like realistic users that are wanting to program, they're not looking to build these little one-off functions. They're doing like these much more complicated flows, and they have their whole code base that things are based on and all of that, which is not this isolated little benchmark. So he's like, that's why everybody gets 90% at human eval, because it's kind of in isolation and separated. My reaction as a more like not PL person was, I was looking at these like doc strings that are pretty long and lengthy that you feed in. And I'm like, I think there's a different problem here in that nobody in there, like even if I wanted this function, this is not how I would prompt the system, right? I would not be giving it, here's a full doc string with all the specification. Like here's two examples of how I'd want to use it. Here's the exact input outputs and their types. That's just like, way over the top. If by the time I have this, I could have basically written that function, right? Like it's as much effort. And so we kind of like started thinking about it, him and me, like, okay, imagine I wanted this function. What would it look like? What would I be putting into the system? And we started, kind of on our own, playing with ChatGPT. We'd know what function it was supposed to output, and we would kind of do this sharding process that we're going to talk about later in the paper, where we would be like, hey, I want a function that sorts things, and then it would like say a lot of stuff. And we'd be like, oh, by sorting, I mean this, right? And the sort of, multi-turn underspecified conversations. And we quickly realized just through inspection that it wasn't getting to the right solutions as often, right? And it was kind of, if it made an assumption early, that assumption would trickle down in the whole conversation, all these things, right? We were very surprised that all the LLMs have this problem basically on every task. There's slight differences in magnitude, but there's no model that's immune to it.
Interesting. Now, so let's start, I guess, at the very beginning with just some definitions, right? When we're talking about multi-turn conversations, what are we talking about? What are they?
This is actually a really interesting point that you bring up. So LLMs, large language models, they have this ability to do multi-turn conversation. So what does that mean? LLMs, they're still language models. So language models take in a sequence of inputs, of input tokens. Tokens are basically like words, and then they output something. They output a sequence of tokens as well. It's just that most of the models have been trained with special tokens called user turn tokens and assistant turn tokens, and there's also system tokens, but that's less important. But because of this, you could feed in a single sequence what looks like a multi-turn conversation, because you can say, well, there was a user turn, then there was an assistant turn, then there was a user turn, etc. It's all concatenated into one sequence, but it's if the model has learned to deal with the user and assistant tokens well, it can understand, okay, like this represents a multi-turn conversation, and it can produce the next assistant response. And I think like one of the big problems in all of this is that these models have been mostly trained on single turn conversation. I think the LLM companies do have some multi-turn data, but it's much less than the single turn data that they have. There's a lot of analysis that shows that a lot of the corpora of instruction tuning and things like this are focused on single turn, which means that though the models might be able to generalize to multi-turn conversation, we don't know to what extent they can, right? And this is what there's more and more body of work trying to study multi-turn interaction and multi-turn conversation, and we're kind of part of that and showing that things break down. Like it's not like because models can do well in single turn, they can all of a sudden do well in multi-turn.
Yeah.
And I think one anecdote that I'll tell you that I think is really interesting is if you kind of go back to the history of the OpenAI models, the models were all single turn, so they didn't have multi-turn models, at least that I know of, like nothing popular until ChatGPT. So this is like GPT 3.5 Turbo. And before that, the last model before that was GPT-3 DaVinci 003. That was their last largest single turn model. And if you hear OpenAI folks talk about that period, they're like, we were kind of surprised by the rise of ChatGPT in popularity, because in terms of like model aptitude, DaVinci 003 was actually pretty close on par. They just maybe took that model, tweaked it a little bit, and then added this multi-turn ability so that ChatGPT could be like, it's like in the name, like chat, right? And so it's really interesting to me that, though two models, one can be just single turn, right? Like kind of text completion, like DaVinci 3 and ChatGPT, one can become a lot more popular because of multi-turn, like this, oh, you can chat with it, right? And I think that, that's why we shouldn't think, okay, LLMs, it's fine if we evaluate them in single turn, because the thing that made all of this popular is multi-turn capabilities. And nowadays, nobody releases a model that doesn't have this user and assistant turn capability, right? Nobody's releasing text completion models, or like none of the popular models are. So you can't really release an LLM that, though you could release an LLM that can just do single turn, nobody really does that, right? Like everybody releases like multi-turn capable models.
Right. It's not the way it's going to be used in the real world, right? In the paper, just to go back to the history a little bit, which you were just mentioning, you take the time to give us a little bit of background. Like you mentioned, previous generation models trained really on single turn conversations. Then MT Bench comes out. Talk to us a little bit about MT Bench, what it attempted to do, and kind of like where it fell short to where we are now.
MT Bench, MT is for multi-turn. So MT historically in NLP community means machine translation. So there's a bit of a collision here. Nowadays, MT is kind of like the multi-turn term is being used more and more. And they started wanting to evaluate, multi-turn ability. They were some of the first people to do this work. And I think a lot of the work was kind of, just annotation. So you would kind of like sample different conversation with different LLMs, and you'd ask people, okay, do you prefer, at turn 3 completion from model A or from model B, these kinds of things. And it was growing pains. So like I think the first empty bench was only 2-turn conversations, which obviously is now super multi-turn, right? Like it's just a start, and then people starting building out from there and up to 5 turns, etc. And then what we at least frame in the paper is that the main limitation is that prior work has seen multi-turn evaluation and single-turn evaluation as 2 separated things, where they're on kind of like different tasks, right? And basically multi-turn is viewed as this like what we call episodic tasks. So you can imagine, okay, you feed in a document and you're like, can you summarize this for me? So that's turn 1. And then turn 2, you're like, oh, can you also translate it in English, right? Or in another language, right? Then it translates it. And then you're like, can you now like make it into bullet point, right? And then it does that, right? And then like single turn tasks are like evaluate more differently. They're more like reasoning tasks or whatever. But then like with episodic tasks, what we say is you can evaluate at each turn sort of independently. It is still multi-turn in that like you might need context from previous turns. For instance, you might need to read the summary of the document in order to translate it, right? So there's still some dependency, but the evaluation itself happens at each turn, right? So you can evaluate whether you're succeeding in a conversation at each turn because of these like this concept of an episodic task. On the other hand, in our work, we were like, it doesn't make sense to separate things this way because people are doing the same tasks in single turn or multi-turn. At the end of the day, they're trying to get something done. They try in the single turn. If it doesn't work, they keep talking until they figure it out, right? And so we were like, this episodic evaluation is kind of limiting in that sense. And so we framed this setup where we say, hey, like evaluation should be done conversation level, right? Like you're trying to achieve this one objective, and the conversation is multi-turn because it's underspecified. You're trying to achieve this task over time, and it's not like each turn is a different subtask, right? It's like it's just like one big task that you're trying to accomplish. And I think that's a little bit more realistic. Like we're trying to kind of like try to move towards like more realistic evaluation of like it's conversational level thing rather than turn level evaluation.
One more definition, UnderSpecification. It's a linguistic concept, but it's tied to multi-turn accuracy.
Right. UnderSpecification is like, you have a fully specified task, right? Which has all the input details so that you can obtain the output that is the end goal of the task, right? So when we were talking about human eval, if you have the full doc string of a function and you have the function header with all the name of the function and the inputs and what the outputs are, and you have, few shot examples as to what are the inputs and outputs specifics, that's a fully specified instruction, right? On the other hand, if you provide any subset of that information, but, there's still crucial elements that are missing, then, if you provide that underspecified instruction, there's no way the LLM can accomplish the task for you unless somehow it, hallucinates the right missing information, which is not impossible, but it's obviously much harder. And the idea is like in a situation where, underspecification happens in a conversation, you don't necessarily want the LLM to just prematurely try to fill in all the gap and try to produce an answer. You might want the LLM to efficiently help you navigate, okay, what have you not yet specified that we need to figure out together before I, produce a solution for you? And why do we care about underspecification? We care about underspecification because there's studies that show that in logs of AI human conversation, underspecification is fairly prevalent. So there's a study actually from my group at Microsoft a year before I joined that showed that, so we did an analysis of all the Bing chat logs. So Bing chat is like this, basically like a chat GPT within Bing that you can use for free, and millions of people use it. And then they kind of studied the logs to see, okay, how often, we got to a final solution at the end, but like at the start in the first few instructions, there was not all the information needed to get to that solution. And they showed like maybe 40 to 45% of conversations in big chat logs, there's some level of underspecification. And what I want to point out is, why does underspecification happen? For me, there's two main reasons. There's probably more. And, like you said, it's been studied in linguistics, and there's probably more thoughtful theory around this. But one is that in general, humans are lazy. Typing has an effort cost, and you're not going to put in effort, unless you need to, right? So, and I think this is something fundamentally different between human to human communication and human to AI communication. So if you look at the code setting, people that say have human to human communication about code, they might say, go to GitHub and put a GitHub issue about a problem they have, right? And they're going to tend to fully specify everything. They're going to be like, here's my problem. Here's everything I've tried so far.
Here's a picture of the error message. Right?
Yeah, here's my OS number. Here's exactly. And why do they fully specify things like this? One is social norms, right? Like, you don't want to waste people's time by not giving them what they might need. And two is there's very high latency, right? Somebody might only get back to you in 3 days. So if they get back to you and they're like, I need to know your version number before I can help you, then you've just wasted 3 days, right? So you have a tendency to like really specify things fully, both to be polite and to respect norms, but also to kind of like maximize your chance of like getting your solution quickly. On the other hand, obviously AI has very low latency, right? It gets back to you in seconds. So there is a very high cost for you to keep typing and think, okay, what else would I need to provide? And there is, ideally, if the system comes back to you and is like, within seconds, we also need this and this and this, you're like, okay, since you ask, I will provide it, right? And then the second thing is that, and this was pointed to me by members of my team, is the most interesting case of underspecification is you're working on a problem that you yourself haven't, as a user, haven't figured out what the full specification is, right? So sometimes you approach a problem and you have some elements, but you haven't thought it through. Like, imagine, I don't know, you want to buy a new vacuum cleaner for your house. You haven't thought about, like, what are all the dimensions? Do I want cordless or not? If I have a lot of carpets, how does that matter? These kinds of things, right? And it takes like a good salesperson to help you navigate the space, right? Ask you all the right questions. What's your budget? All of that, right? And so I think like the most interesting case for like this human AI interactive collaboration is when you don't even know what the full specification is, right? These problems that are underspecified in your mind, and part of the conversation is to tease out the full specification out of you, right? And like the nice way of saying it is, AI sure can help a little bit when you already know the full specification, and you're just a little lazy, so it has to help you just like write it out. But it like the value seems much more vast on problems where you yourself don't even know the full specification, and you need this like partner to help you figure it out. And so that's why I don't think, it's just a matter of like, if we had a way like people just not type, but like, it would read your full specification out of your brain, or you could speak it out. So like we lower the barrier to, kind of getting better instructions from people. That would still not help in that second situation, which seems more important, where, at the end, like interaction is sort of necessary to solve problems that, if you haven't fully thought it through as a user.
Right. You don't know what you don't know. And
yes,
it asks you the questions to kind of help navigate that. Okay. So first, your paper is called LLMs Get Lost in Multi-Turn Conversation. Tell us a little bit about your approach to multi-turn accuracy and what you all did differently.
Yeah. So based on a little bit of the motivation that I explained a few minutes ago, we were thinking, okay, we have very high quality single turn benchmarks, right? Like for many tasks, which have their evaluation set up that is, good evaluation. So like if you're doing, Python programming, they have unit tests that you can run on the generated functions to see if like the solution is correct or not. Or if you have text to SQL, you can take the SQL and then run it on test databases and see if it returns the right thing. For different tasks, people have very good evaluation. And we were like, okay, what if we could reuse these somehow, these like instructions in single turn setup, which we call these fully specified instructions, but leverage them to simulate multi-turn interaction that would occur in an underspecified way for the same problems. And what would that allow? We would be able to observe, okay, on the exact same task, what is the performance if you provide everything in the first turn versus what if you provide things gradually? So in order to do this well, we had to build out this like little user simulator, right? That would have this instruction and would not blurt out everything all at once, but kind of like speak things, one turn at a time, provide a little bit more information, and kind of act as a like lazy user that underspecifies things. And we played around with different formulations of this, and we found that the best way to do this was to take the instructions and to apply this sharding process. And basically the sharding process, if you think about it, like you have a fully specified instructions, and we're going to find a set of shards, so a set of smaller instructions, if you want. If you take them all together, say the exact same thing as the fully specified instruction, but now they've been split into smaller pieces. So that basically once you have a sharded instruction, like say you have a fully specified instruction and you have its equivalent sharded instruction might have, say, 6 shards. Right. Now you can use that like pre-processed version of the instruction and a very lightweight user simulator to basically pick what shard to say at what turn. What I'll say like very quickly is, when you do this, you have to make assumptions about users. And we made like these very benign assumptions about users, so for instance, we made the assumption that the user will reveal new information, so a new shard of information at every turn. Well, that's not necessarily the case in real world settings, right? Like users might get frustrated and end the conversation, or they might say, I don't know, and I don't think that matters, right? They might like say all sorts of things, right? Or they might say incorrect things. They might like, disagree with what they said earlier and be like, oh, actually, I don't think we need this requirement anymore, right? So things can get very nonlinear in real world multi-turn conversation. But we have this very benign setup where we know the 6 shards. We know that if you provide the 6 shards, by the end of it, you have all you need to produce the solution, right? And we can just like simulate this little conversation where we have, the assistant trying to help you out. And then at each turn, we have a user simulator that figures out, okay, like at this stage, what shard should I reveal next? And then like just picks that and sort of rephrases it a little bit just so that it feels natural in the conversation. But that's sort of like this very benign setup that we have. And then, we're going to probably get into the results soon. But like the high level is, even in this very benign setup, all the models we tested, their performance in this like sharded simulation setup drops around 35% compared to their, like fully specified single turn evaluation.
Right. And so you can imagine adding in any kind of like of the real world complexities of multi-turn conversations that could even,
make it much harder. Yeah. I think like that's the claim we try to make in the papers. Our estimate of like degradation is an underestimate. Right. We imagine that with real world situations, things are actually becoming much worse. Now, okay, that's just a hypothesis, that seems kind of natural to think that.
So you have 7 possible response categories. Talk to us a little bit about those and how you came up with those categories and kind of what you're looking at in each one.
Yeah. So, we actually borrowed this from prior work. So prior work had kind of like studied what are the response strategies of LLMs and maybe how do they differ across different models? And, because like you would imagine that like different strategies will lead to varied performance by LLMs. So let me try to like kind of like list all of them. The most common one is this concept of answer attempt. So, you say, I need a Python function, or I need an SQL function, or I need, a summary of documents or any, output that you're looking for. And the model produces this free text response, right? So it might say, great, I'm happy to help you and all of that, right? And that's not part of an answer attempt, right? Like if it just writes, something like a greeting or something like that, that's not an answer attempt. But then it'll put something in some code block, or it'll say, the final answer is 28 or whatever, right? And that's what we consider an answer attempt. So basically, if the original problem is the final answer is a number, or the final answer is a block of Python code or whatever, we basically look for that in the answer. And if we find a match, then we say, okay, this was an answer attempt. Okay. So from there, you might be thinking, well, everything's an answer attempt. So no, there are things that the model might do that aren't answer attempts. So here's some of them. So the model might ask a clarification question, right? It might be like, well, you're asking me to write a Python function, but I don't know what the inputs are. So maybe tell me the inputs before I proceed producing, an answer. And if it just does that, that's clarification. Or it might ask you a barrage of questions. Like we say, like an interrogation is like if there's 3+ questions. So it might be like, I need to know the inputs, I need to know the outputs, I need to know the edge cases, I need to know, and when it starts structuring it like that, we call it an interrogation. I think it's a bit of a fine difference between clarification and interrogation, but we still kind of like split it up this way, following the prior work. Another thing it might do is hedging. So hedging is like, imagine that you haven't specified something. It'll produce an answer attempt for each of the possible conditions of that thing that you didn't specify. Mm-hmm. So imagine you're like, I want a function to do this, and you didn't specify Python function. Then it might be like, oh, if you want it in Python, this. If you want it in JavaScript, this. If you want it in Java, this. And so it's called hedging because there's multiple kind of if and else statements. And so that tends to be these very long responses, right? And you don't necessarily know which one is the answer attempt. So we call that hedging. Missing is when the model just doesn't answer, which is kind of more of a technical error thing, but it does happen. So we categorized it. And then refusal is also interesting. And the model might, it's a fine line between clarification and refusal. The model might say, but it might be more negative. Instead of asking a question, it might be, I cannot answer this because you have not told me X. So in those cases, we tag that as refusal, but I think, it could be slightly rephrased and be like, can you provide X? And then that would be a clarification question. So I think like refusal and clarification are a little bit like the positive framing and the negative framing of the same concept. When it goes into refusal, what we notice is it'll, like, as long as the thing is underspecified, it'll keep refusing. It'll be like, no, you still have not provided X. You still have not provided Y. Okay. And so it kind of goes into the refusal mode sometimes.
Right. All right. You've alluded to it, but you didn't just test this with like coding, come up with, function questions. You tested across five types of conversations. Talk to us about that a little bit.
Yeah, so, I'm more of a natural language NLP researcher, and Hero is more of a programming language researcher. So we kind of built that as a spectrum. And we selected tasks that were like full PL tasks. So that's like, based on human eval or live code bench, which are these like, Python programming problems. Then from there we went to, I think, okay, I'll try to do it in order. So then it's natural language to SQL. So we call that database, right? So it's still somewhat programming, but it's more on a database rather than like code. So the task is you're given some natural language query from a user, and you have to help them, write the SQL query that would find the data that they want. From there, the next one is called actions. So actions is based on the Berkeley function calling leaderboard. And it's basically, here's a bunch of APIs, so access to different tools. And here's a natural language query. Can you help the user, get to the right API call that would achieve their objective? So it's still programmatic, but again, like now it's becoming more like about using tools rather than using programming. And then from there, we did math and reasoning. So we use GSM-8K, which is like a very popular kind of benchmark, where now it's like, you have a math problem and you're trying to find a mathematical solution to this like arithmetic kind of problem. So we're starting to move into natural language, but it's still about math and reasoning, so a little bit still logic. From there, we have a data to text task. So you're given a table and some metadata about the table, like which page it was on, information about like the different, say, headers of where it is on the page. And then you have to write a caption for the table. So it's like a data to text. And then the final one is a pure natural language task. It's just summarization. So you're given a set of documents. You have to produce a summary for that document. Okay. So all of these tasks, what's in common is that they're generation tasks. So you have to produce an answer that's not just like, extract a little, snippet from the original answer. You have to produce this generated answer.
Okay. And we're going to get into the results next. But first, can you explain the metrics you selected? So average performance, aptitude, and reliability. What specifically is each referring to, and why are those what you were looking at?
Yeah. So I briefly said earlier, models, if you use them in singleton, they do really well on these tasks. That's partly why we selected them. We didn't want to select tasks that were really hard because we were trying to observe if it can do it in singleton, can it do it in multi-turn? And so then what I describe is, like a performance drop on average across these 6 tasks, across most models of 35%. But that doesn't tell you about why this happens. And we were really curious to know, okay, singleton, multi-turn. We're doing the same tasks, but we're seeing a drop. But why is the drop happening? Imagine that you were doing 100 different instructions, if you want. Is it that like some of the instructions that you used to be able to do in single turn, now you cannot do in multi-turn anymore? Like they've become sort of out of your aptitude zone? Or is it that like you can still more or less do all of them, but not as reliably? So, like some of them that you used to be able to solve very reliably, now you're like sometimes solving them, sometimes not solving them, right? So this relates to like the aptitude of the model versus the reliability of the model. And in order to study this, you have to take a single instruction and run it and simulate conversations multiple times. You cannot just do it once, because if you do it once, then it might fail, it might succeed, but you don't observe reliability. Right? So this is kind of like the new thing that we did in this paper, which is, we had some set of instructions, and for each instruction and for each like conversational setting, right, single turn, multi-turn, we simulated 10 conversations. Now, why don't people do this previously? Because doing this essentially increases your cost by 10x, right? Like if you had a, whatever API budget of like $1,000 to run your experiment, now you need $10,000 to run the exact same experiment. But what do you get from this? You get to observe the variance that occurs, in solving the exact same instruction. And what's striking is that, going back to the last two metrics, so aptitude and unreliability. So aptitude is, I just ran 10 simulations with, one instruction, one core instruction, say in single turn, and I have now 10 scores, right? I sort them by the score and I take the top 10 percentile. What is the best case score? Essentially, that's aptitude. Can I solve it even 1 out of 10 times, essentially, right? On the other hand, unreliability is a difference. So it's, what is the score in my best case scenario? That's aptitude, minus what is the best score in my worst case scenarios. And we measure this gap, right? And that tells you, if you have 10 users coming in with the same problem to ChatGPT, what is the gap in experience that the luckiest user and the unluckiest user will have, right? It was very important for us to understand, when you move to multi-turn, is it that models just lose aptitude? There are certain things that the models cannot do anymore. Like they get 0 out of 10 on a bunch of tasks that before they were getting maybe 8 out of 10 success on. That would be a very interesting finding, because we could tell people, hey, if you're trying to do this and this and this sort of task, forget it. Like it just doesn't work in multi-turn, right? Or is it just an unreliability problem that it can still do most of the same things? It's just that it's more unreliable, right? So the finding is in the title. It's the models get lost in conversation. It's not the models lose aptitude, right? So basically in multi-turn, sometimes they will make a wrong assumption. And because of that, they'll get lost and they don't recover. They don't like unwind that assumption and like come back to track. So the finding is, as long as they stay on track, they have the same aptitude. So if you sample 10 conversation, there's sometimes one where at each turn, it like somehow stays right on track and it gets to the final solution, right? But as soon as something goes wrong, it just gets lost and it doesn't recover. So it's really an unreliability issue and not an aptitude issue.
Right. And that's across LLMs, across all of the different models. So tell us, let's talk about the results. What did you find surprising?
Yeah. So there's first like a big table that's just focused on average performance. And it shows, I skipped a little detail here that might interest you as well, which is, you can do the single turn conversation just with the original instruction, or you can do this experiment called the concat experiment, which is you take your sharded instruction, which, remember has like these, say, imagine 6 shards, right? And then you concatenate them in a bullet point list. And then you say, here's an instruction. You have to take all of this into consideration. And now that's a single turn instruction. That's just a concatenated version of the sharded instruction. So we actually do this like comparison between running with the original unmodified instruction. This is called full. Then running with this concatenated single turn instruction. That's the sharded instruction concatenated, or the sharded experiment, which is this full multi-turn simulation where you reveal 1 shard at a time per turn. And why do we need concat? Because, when we do the sharding, some things get rephrased, right? And it could be that in this rephrasing, you lost crucial information, right? And so the one reason to explain a drop in performance would be like, hey, Philippe, you made some of these instructions infeasible now because you removed information that was necessary. And so that initial table shows this, that like, performance is great in the fully specified with the original instructions. Performance is almost maintained in concat. It's like maybe on average models get like 95% of the same performance. And then you have this like big red zone, which says, okay, like performance in the sharded mode, on the other hand, degrades very heavily. Right. And this is across the smallest, open source models like, Llama 3.18b, all the way to like, at the time we tested, we really made an effort to test all the models as they were coming out. So Gemini 2.5 Pro and Claude 3.7, I think, is the last ones that we evaluated. And then, the GPT 4.1, 03, etc. And we have been internally testing the new models, and it's still more or less the same, though that's not in the paper.
So they get lost, right? But why?
And we have a whole section that unfortunately now is in the appendix of the paper, which is called this like qualitative analysis. And we try to understand some of the reasons why these models get lost. The first one that we find is that because we simulate multiple conversations for the same instruction, for the same model, we can see, okay, when did things go right and when did things go wrong? And we can kind of try to infer what are the types of statistics that lead the models to get lost. So one thing we observe is, the models sometimes, if they're smart, they will ask a few clarifications at the start before they make an answer attempt. And what we observe is, for all models, the later they do these answer attempts, the better they perform. So if they can hold out somehow in these multi-turn conversations, instead of like jumping the gun and like, here's a solution when, you've provided only 1 out of 5 shards, like nothing is said yet, right? The more it waits it out, maybe by refusing or by hedging or by whatever, the better it is for it to kind of perform well. So that's one. The second thing is we show that the shorter the answers that it writes, the better. It's kind of a simple finding, but the instruction, though it's like multi-turn, it's just one sequence of like tokens that are separated by user tokens and assistant tokens. And as we know, LLMs are very chatty. So the user might say 10 or 15 words, and then the LLM will write 400 words, right? And so if you think of that record of the conversation, it's mostly assistant tokens, right? So the longer it talks, the more it's disproportionate, right? If you look back at the conversation, it's mostly assistant tokens and less user tokens. So the finding is the shorter its responses are, the better it performs, which means the more it talks, the more it's likely to put assumptions down. Oh, let's assume this, let's assume that, like maybe you mean this, maybe you mean that, right? And then later on, that's going to confuse it, right? Because it's maybe you're going to clarify something, but it's going to clash with something that it assumed or something like that. And then that's going to hurt its performance. The third one is that we show with like one specific task that the LLMs tend to focus most on what you said in the first turn and what you said in the last turn. And that the turns in the middle, say you're having a 4-turn conversation, and say at each turn you're providing crucial information, it's going to tend to disregard things that are, in turn 2 and 3 and focus mostly on what you just said last and what you said at the very beginning. And of course, like that's problematic because, if you don't want it to forget crucial information.
Well, now, so are those things that can be sort of embedded into the model design to kind of curb the degradation of the multi-turn accuracy?
Yes. So I think this is one of the pushback that not pushback, but like conversation we got on social media when we released the work is people are like, but you could have just told the LLM at the start, I want you to ask like 3 clarification questions before you proceed with producing an answer. And, based on the qualitative analysis, sounds like that would lead models to not get lost as much. And here's our view of this. When we evaluated the models, we told them as little as possible about the situation they were in. We didn't tell them, we're going to simulate a single turn conversation and you have to give your final and best answer now. Or like, on the other hand, you're in a sharded multi-turn underspecified conversation, so be aware the user is extra lazy and you might want to ask clarification questions. Why didn't we do that? Because in practice, if you host chatgpt.com, a user comes in and you don't know whether the conversation is going to be underspecified or not, right? You don't know how conversations go in general. I kind of like alluded to this on Bing chat logs. 45% of conversations have some level of underspecification, right? So if you tell your system, ask 3 clarification questions before you proceed, For the people that fully specify things and that expect a fully formed answer by the end, it's going to be a terribly frustrating experience that they're like, here's an email, can you make it more, like I don't know, more formal for my boss, and it's like,
Right.
who is the audience and what, like, like asking these things that you don't want to experience. So I think fundamentally, it's for the LLM to figure out what kind of situation it's in. We humans, we have to figure out when we're communicating with people. If somebody asks me, Philippe, can you share the code with me? I have to figure out, do I have enough information that I know what they need, or do I need to ask, like, do you mean for this project or that project, right? Like, I have to dynamically figure that out, and that's the point we make is LLMs, by their default behavior should be figuring it out. Of course, you can tweak it to, do it well, but just that behavior, but that's not really what you want.
I think it's worth talking about the 2 reasoning models that you included, O3, DeepSeek, R1.
So we tested both non-reasoning models and reasoning models. So the background here is reasoning models, what they can do is they have a phase where they still generate a response, but in that response, they have first a thinking phase where they can basically write their internal thoughts before they then end the thinking, and then they start giving their official response to the user. And our original thought was, if we don't include these, people are going to say this is solved by thinking models. And why would you think that it could be solved by thinking models? Because imagine a thinking model in a multi-turn conversation might be able to see what the conversation so far is. And during the thinking process, it might be able to say, okay, the user has said this during turn 1, this during turn 2, this during turn 3. Let me concat it somehow, right? Concatenate it, or let me like rephrase it into a fully specified instruction, and then might be able to actually close the gap on its own dynamically, right? And basically be able to solve the problem in a much more reliable way than, a non-thinking model, which just like blurts out without having this step of consolidation. So we were very worried about this, because we didn't know the way it would go. And we were like, we must test the best reasoning models and see, do they close the gap or do they not close the gap? And the great finding for us is that, thinking models don't close the gap at all. They have similar deterioration of performance. We didn't study this like particularly in depth, but we did look into the outputs of all the models. And the one thing we found out is that reasoning models tend to write longer responses than non-reasoning models, because they tend to, think a lot, plan like, okay, my response will have this, this, this. And so they tend to put out, I think, more assumptions out in their response than their non-reasoning peers, which ends up hurting them a little bit more.
So I'm kind of jumping ahead a little bit to the implications, I guess, because I'm curious, yes, it could be fixed maybe by a user sort of, I don't want to say user interface, but like somehow kind of controlling what and how a user enters information. Training, I guess, on multi-turn conversations, which you state in the papers. How else could you improve model capabilities or multi-turn capabilities for these LLMs? What are some ideas?
Yeah, I think like it gets a little philosophical, honestly. At least like we had this kind of philosophical question. I remember as I was presenting the work before it came out to a few friends in LLM shops, they were like, oh, it's interesting that you evaluate like these base LLMs on multi-turn conversation, because internally some of these groups have moved to evaluated agent frameworks in multi-turn settings, but then base LLMs only in single-turn settings. And I think like the claim in our work, and I think my personal assumption is that agents are sort of like like a set of complicated system on top of LLMs. But I think fundamentally we want the LLMs themselves to be capable of multi-turn interaction, right?
Yeah.
Like you can see it like with the story of like going from DaVinci 003 to ChatGPT. All of a sudden that model is used by hundreds of millions of people, right? And so I think at the core that this is like what we hypothesized in this paper is we want to make multi-turn evaluation a first-hand citizen of LLM evaluation, and not an afterthought, or not this is for the agent people to figure out. So we have a few experiments of like testing out basic agent frameworks and showing, hey, this doesn't solve the problem at the root. And I think like this is a little bit like what kind of AI systems we'll have in the future. Maybe they won't be monolithic LLM systems, right? Like they won't be just like a transformer trying to do things. Maybe it'll have memory and tools and things like this. But I think it should be still down to the basic blocks to be able to have an LLM figure out, okay, at this stage, it's still too underspecified. We're still at the phase where we need to like help the user navigate the space before we drill down to a solution, right? That's still like a decision that needs to be made by the LLM. I don't think an agent framework that like pieces things together is going to be able to do that. So yeah, I think like for me, I hope that we get base LLMs that are much more capable at natural interaction and natural multi-turn conversation. I think that's the road that we should go down. And this is the other thing we argue in the paper is a lot of work recently has focused on aptitude. So remember, aptitude and reliability are these two kind of like axes. And like to give you a sense of that is like, we have harder and harder AI benchmarks in terms of like intellectual difficulty of the problem. So there's a problem, like there's a benchmark called a humanities last exam, which is like all these very technical PhD level questions that were curated by PhD students, in their field of study, like very sharp, hard technical questions, right? Or you have, the math Olympics or something like this, with like these like very hard math questions that are almost research math questions. And we're trying to show, hey, these LLMs, if you do a lot of thinking rounds, one of them will produce the solution, which is just like this incredible thing that like this model is capable to get to solutions. On the other hand, in a lot of these benchmarks, the way they evaluate is like, even if in 1 out of 20 rounds it gets to the correct solution, it gets full credit, right? But like what we argue in this paper is like optimizing for this aptitude is not good for the average user, right? Because the average user, we get very confused. We use a system to do a task. And if it can't do that task, then we think it's an aptitude problem. We think, oh, maybe ChatGPT can't do whatever, Arabic translation, just because it doesn't, it didn't do it well once. And then we just give up. We're like, okay, like this kind of task, I will not try again, maybe until they release the next version of the model, right? Because we conflate like unreliability to basically an aptitude problem, right? On the other hand, I think like if the models were more reliable, then you would, as a user, have a much better sense of what the model can and cannot do, right? And that would really help with usability, right? Like people would be like, well, tried it for this, it worked. Now I can expand. I can like keep trying new things until I hit the aptitude limit, right? And so I think like we shouldn't sleep on reliability. We should like really optimize reliability jointly with aptitude. I think AI folks, we get very excited about, wow, we got a model
to do this.
Yeah, to do this like even once. That's incredible. We found a way to train a model to do AlphaGo. Wow. Like that's, and I of course like I get excited about these just as much. But I think we need to lift the average bar and not just like the top of the percentile, right? So that's the big call to ours that we had in the paper of like we need to jointly optimize reliability and aptitude.
Now, just out of curiosity, as a user, as like an average user over here, if I were to do my own little experiment of 20 times asking the same prompt the same way, will I get 20 different responses?
Yep. You should try it out. This is like this is what's very surprising is that these language models, they're statistical machines, right? They're producing words in like, according to a random distribution that they produce. That's what a language model is. And we use LLMs at temperature, typically a pretty high temperature, at temperature 1 or temperature 0.8 for most of these providers. And what that means is that there's a lot of randomness in the generation process. And, I feel like as like our society doesn't understand randomness really well. There's all these studies that show people get confused about probability or conditional probability and things like this. And so I think that's the really confusing thing is sometimes you ask the LLM something and it responds like totally off. And then people like now they're better at switching. If you try on ChatGPT and it doesn't work, you try Claude and then you try Gemini, and I think that's great. That's a way to kind of like see what different models will say. But actually, you could just literally refresh and ask the LLM multiple times, and it'll come up with like significantly different things, right? And I think that's something that is really something we don't think of like as very natural as users. To give you a very concrete example, when I'm working on like some of the marketing of my paper, like what would be the name, what would be the title, what these like the crucial elements to the paper, I often get help from LLMs. Maybe I have an idea and I'm trying to brainstorm more or something like this. I will ask it like, give me 10 ideas. than it does. And I'm like, okay, refresh. Like, so you can just like keep getting it going. And then sometimes then I like one, and then I will start a second turn. I'll be like, I like this one. Do you have 10 more of that one, right? But I feel like,
Right.
like this notion that you can sample from it, is like really underappreciated. I think people do it a lot more with images, so you give it a prompt and you're like, okay, draw
Yeah.
this with this with this, and people will want multiple samples because they're very easy to review, right? Like you can visually see 8 and be like, I like this one most, right? But people don't do it as much with text just because reading text is a lot of effort, and you think it's going to just say the same thing. But it's exactly like the image situation. It's actually generating very different answers, right?
All right. And so you mentioned already sort of your call to action to LLM builders, which is prioritizing reliability. But you do include in the paper sort of the implications for users. Can you share a little bit about that?
Yeah, this is the wonderful thing that happened with this work is we put it out, and you never know the reception to an academic paper, like it's very nerdy stuff. And we got this like great reaction from people who use Cursor and code editors. Like that's one of the main use of AI these days. At least it feels like that. It feels like it's very important. A lot of people are like, if you've used Cursor just for 30 minutes, you know of this problem. You felt it, right? Like as you chat with it, things get worse in the conversation. And, we had like these quotes from like forums of Cursor users. Somebody had asked, how often should I start a new conversation? And some of like the most upvoted answers are like, as much as you can, like you got to start a new conversation as much, like, as often as you can, right? And this just shows people are kind of they feel it like, man, like it's wasting my time. Like I'm asking for the same thing again and again, and it keeps like editing it. But if I just start from scratch, somehow the solution is much better, right? So that's the effect that we describe. And so practically the way we tried to make it into two formal recommendations for users. One is actually what we just talked about, which is don't think because you had one conversation with an LLM that it necessarily relates its aptitude, that it cannot do this task if it failed. You might want to try again. Even with the same LLM. Of course, you can try with other LLMs as well, because then like you're mixing it up a little bit more. But even with the same LLM, you can just like rerun the query, see what it comes up with the second time. It might be better just because it's like sampled down a slightly different path. But then the more practical piece of advice I have is like, try to consolidate what you want, as you figure it out, as you see bad solutions from the LLM or bad things and like, no, actually, I want it like this, like that. Try to consolidate that and then start a new conversation with that consolidated instruction. You'll get much, much further. And the way we even say it is as you're having a conversation and you feel like the model got lost, you can ask the LLM, hey, consolidate everything I've said into a nice little instruction. Because it'll be able to do that. Like it's not lost to the point that it can't read. Like if you explicitly ask it to consolidate things, it's going to do it. Then you could take that instruction and start a new conversation. If you're like a little bit like, oh my God, I'll have to scroll and like copy paste things and then like restructure, the LLM can do that for you. So I think like literally, I imagine and like at least temporarily until LLMs don't get lost, these cursor interfaces, they're going to have, they used to have a warning, like when the conversation got too long, that was like, careful, you might want to start a new conversation, right? And I think they've removed that, but they might have a button that looks like we're lost. Just click a button and it'll start consolidate and start new. So I think these sorts of things are hopefully going to appear and make it much more, straightforward to do these things.
Little hacks.
Yeah, until we get LLMs that are just, they don't get lost.
They're going to do it.
Right? The way that people interpreted it online, which was really wonderful, is they're like, prompt engineering really matters. Prompt engineering is not dead. So I think there was this framing that prompt engineering is less and less important because we're getting better models and they can just like read our minds and whatever. And this is a way to interpret our work is your first instruction matters a lot, right?
Yeah.
If you just say something very underspecified, because the model is more likely to get lost, you're wasting your own time. So if you think a little bit more and consolidate your instruction before you send it, or, if you've gotten lost and then you consolidate and start over with this more prompt engineered instruction, you might do much better. So I love a lot of people are like, prompt engineering is not dead. This work shows it. And we were like, okay, that was not really at all what we had in mind, but it is a correct interpretation of the work, I think.
All right. So then the limitations, we talked about some, like briefly mentioned some, but what are some that kind of jump to your mind as the limitations of the study?
I mean, the main one I think that I want people to be cautious about is the fact that our user simulator, like we talked about, is very like this very benign thing that is very simplistic, you know? So I don't want people to think, you know, we've actually released a corpus of here are all the sharded conversations with all of these models, and you can kind of explore them in a little website. I don't want people to look at that and be like, oh yeah, these are representative of real conversations in the wild, because they're totally not. You know, they're very simplified and they feel very robotic. So in some sense, what we've done is that on the spectrum of studying, you know, human AI interaction is very on the automated way. So this is like an automatic probe to measure that we would think in this very benign setup, performance should be the same, but it's not. So it's a lot more a statement about the LLMs failing than about how users communicate and things like this. Like, you know, we got some questions like, well, would users really shard this way, or would they shard at a different granularity, or like, what are the properties that you've made assumptions about that are incorrect? You know, and we are not making really claims about that. We're just saying this is a valid way to shard. You know, we prove with experiments that we don't lose information or things like this, and yet the LLM performance drops so much. That's curious finding about LLMs. So I think like as we make progress as a field, we need better user simulators. And this is like a field that's at its nascency, right? Like in order to evaluate LLMs in multi-turn settings, we need to be able to generate these user turns, right? And so we need more effective ways to do this, right? So I'm very interested in this. You know, we have a couple of people at MSR working on this. Like, how do we build better user simulators that take into consideration all the complexity and stuff that can happen when users communicate with AI? And so, yeah, I think that's a big limitation of this work is we made very crude assumptions there. And, you know, hopefully future work will make it much better and be like, see, the performance degradations are even worse, you know? So that's my hope. And then what else would I say? I mean, the other thing is we focused on English tasks. So, you know, degradation is probably worse on other languages, most likely. And then we focused on, I would say, like more tasks that are easy to evaluate. So these more analytical tasks, you know, where there's often a correct answer that you can evaluate. Now, you know, does that mean that models don't get lost on more open-ended tasks, like, you know, creative writing or like, you know, just general writing tasks? Not at all. Like, I think probably they get even more lost because it's even more open domain. But we didn't show that, partly because evaluation there is harder. And we were like, you know, first paper, we kind of like set up things in a pretty like, you know, straightforward way. So I think it's just kind of an opening to this general direction of research.
Okay. Now, do you have future work coming out about related to this work or any other work coming out?
I'm actively continuing this direction, both with Hero, so my collaborator, and we have some internal projects going on. So I'm hoping that we're going to work on better user simulators. We have some seeds of projects. It's just starting. I think it's going to be a brand new field, you know, of like how do we evaluate these models with good simulation, right? So I feel like in robotics, they have very good simulation environments, right? And they test models a lot in simulation environments, right? And self-driving cars, you know, we know the better your simulator, the better the model does in the real world, right? And maybe that's what we need for LLMs as well. We need these like, you know, simulation environments where you can simulate conversations that are much better than the sharded ones we have, right? And you can be like, oh, wow, the models still get lost. Or no, all these kinds of things that you'll find out if you have a good simulation environment. So, you know, I think like that's kind of an open field. Like I think there will be many PhD students studying this, hopefully in the coming years. And so, yeah, I'm doing a little bit of work in that space. And yeah, I have one project around, can we make the model more reliable? So when it does get lost, are there paths, you know, can it generate responses that get it back on track? If so, can we encourage it to do these things? But we'll see, you know, it's research. You never know what will work and what doesn't. So yeah.
Very exciting. Well, I'm looking forward to staying up to date on the release of those whenever it is. Philippe, we appreciate your time. Thank you so much for discussing your work.
Absolutely. It's been a true pleasure being on the podcast.